Okay, so next question is question 8. And we've got some circuit questions. I'm looking forward to those of you I taught last year. I think you'll do really well on the circuity bits on your mock. We've got a nice basic question here in terms of a resistor connected to a power supply. The potential difference is 6 volts. Which of these corresponds to a potential difference of 6 volts? So this is just checking your definition of potential difference. So we said, well, potential difference, and because this is a higher tier question, we said, well, it's the push from the cell. We said it's the difference in energy between 2 points of the circuit. So if that was 2 volts and that was 6 volts, the potential difference would be 4 volts. Imagine that's a circuit there. Apologies for that dodgy diagram. But we also said it's the volts, whip, queens. It's the work done or the energy done per unit of time, because we see V equals W over Q. And this comes up a lot on higher tier questions. So potential difference tricky because we've got sort of 3 types of definitions to help us understand it. We said it's the push, it's the energy difference between 2 points of a circuit, or it's the work done or the energy done per unit of time. So I'm after something here where I've got energy and per unit of charge. Well, we know charge is coulombs and work is energy joules. So I'm after joules, W, per coulomb. So joules per ohm, no. Amps per coulomb, no. Joules per coulomb, perfect. C. Done. Next one, resistor remains connected for a period of time. The current is 200 milliamps. Okay, here we go. So that's 0.2 amps, and then we're ready to go. A total charge of 42 coulombs flows, so that's Q. So we've got I there, and it says calculated minutes, so we've got time. So as you well know, this is our I quit formula. And then we just got to whiz through it. So we know Q equals I times T. So T equals Q over I. Circle there. Just drop my pen. What a doofus. Next part. So now we're going to do 42 divided by 0.2. It's 210 seconds. You can see, and the final mark is we've got to divide this by 60 to get this in minutes. 3.5 minutes. Done. Next question. Calculate the total. So vultures, whips, queens coming back again. So calculate the total energy. So we've just got to keep remembering that work and energy are the same thing. So I'm going to write a W here. 6 volts and 42 coulombs. So Q, V, and we're going to need that. Vultures, whip, queens. And it wants to work out the energy. So this is the work. So W equals V times Q. Just going to times these together. 6 times 42 equals 252 joules. Next one, the resistor becomes warm. Why? Explain why the resistor becomes warm. So the resistor's got resistance, and the basic idea here is the positive metal ions. So if I was to, we know how conductors work. There's my positive metal ions, and they're vibrating around fixed positions. And then we've got delocalized electrons that can go for a wonder. And what happens is sometimes these electrons will collide with a positive metal ion and make it vibrate more. If we increase the kinetic energy stores, we increase the temperature. That's the basic ideas. So the basic idea is, why is it that resistors become warm? Because they have resistance. Electrons bump into whatever atoms or positive ions are in the way, and this increases the kinetic energy, which increases the temperature. So here's your model answer. So there are collisions between free electrons and the positive metal ion lattice, and that, I can't word that any better than that, apart from maybe put an S in there for collisions. And the next bit is, this increases the kinetic energy stores of the positive metal ions. So the basic idea is these are vibrating, these positive little metal ions here, wiggly, wiggly, wiggly. The electrons flowing through, the current flows through. These electrons will then bump into this. This gives it a bit of energy, makes it vibrate more. And as we know, temperature is a measure of the average kinetic energy of the particles. So temperature's gone up, done. Cardboard tube with a wire coming out of it. So we've got no idea what's in there. There are 2 10 ohm resistors. Okay, so we know there's 2 resistors. So ultimately what it's asking is, have we connected them like this, or have we connected them like this? Oops, that's a dodgy little line there. And if that was a 10 and a 10, and if that was a 10 and a 10, well, we know the total resistance if I connected them in series would be 20 ohms. And the total resistance if I've connected them in parallel will be 5 ohms, because I've taught you that'll be 10 times 10 divided by 10 plus 10, because we know the resistance in parallel is R1 times R2 divided by R1 plus R2. So basic idea is, well, let's calculate it. If it comes to 20, they're in series. If it comes to 5 ohms, they're in parallel. Here we go. So R equals V over I. So 6 volts, which is there, divided by the 1.2 amps. Perfect. The resistance is 5 ohms. Let's have a quick look. Yes, that one there, job done. So the resistance is half of the individual value. So the resistors must be connected in parallel. That's that one done. And I can now go and rescue my pen that's gone behind the radiator.